Good evening. So the name of this talk will be Functionality 6, Creep Resistance. I am Javier Belzunce, Professor of Material Science Engineering of the University of Oviedo, which is placed in northern Spain. I have divided this talk in these 4 topics. First of all, I want to give you some idea about the importance to develop new high temperature materials, because there are many industrial fields where there is a real necessity to obtain new materials who have a better performance at high temperature. And then secondly, I am going to give you some brief ideas, some overview about what is creep behavior, which are the most important creep micromechanisms, and also to give you an overview of the micromechanisms maps we can use in order to develop these new materials. Then I am going to give you also some practical examples of material development, and to finish with the conclusions. First of all, I am going to start this talk giving you an idea of in which fields that is very important to develop new high temperature materials. Let me give you some examples. This is, for example, a coal-fired power plant. In this case, as you see, we use coal, pulverized coal. We put this coal on the boiler, and then we obtain electricity. Following this scheme, the way to do it is this coal is put it here in the boiler, and then there is an entry of air or oxygen in order to make the combustion of this coal. So there is a high temperature is developed here in the boiler. And then there is some tubes here where water is coming in. This water is heated to make steam, and this steam with a high temperature and a high pressure goes to expand in a steam turbine, which makes rotate the generator, and the electricity is made. So the most important point in this plant regarding to materials is the tubes which are working here in the boiler, because they are submitted to very high temperature and also to very high pressure. This is the goal we have at the moment. So the new generation of coal-fired power plants, which name is advanced ultra supercritical power plants, the goal is that these tubes have to work at 760 degrees C and 35 with a pressure of 35 megapascals. This will be an increase from 35% to 46% in efficiency regarding the situation that is nowadays. So this is an 11% increase, and this, of course, will be a huge amount of energy which can be produced using the same resources as we are using at the moment. If you take into account, for example, that power plant like these ones, there are thousands in all over the world. So the problem is the availability of materials which can support these extremely high conditions. So materials with high creep strength, corrosion resistance, fabricability, and also low cost, because at the moment there are materials who can cope with these conditions. But the problem is that these materials are very expensive. So we need to develop materials in this area, but also which may be low cost. At the moment, ferritic steels are the most used materials in this application. A second example is regarding to gas turbines. These gas turbines are used in airplanes in order to fly the airplanes. So this is a general view of one of these gas turbines, and the problem I am going to show to you is the manufacture of blades which are placed in the highest temperature of these turbines. The temperature will be much higher than 1000 degrees. In this case, as you can see also in this drawing, you can see that the thermodynamic efficiency of these engines are directly related with the temperature which can be attained in the hottest point of this engine. In this case, you can see that the vertical axis is the kilowatts developed per kilogram of air, being all the other conditions the same. So here you can, it's very easy to see that it's very important to go to the highest temperatures in order to have a higher efficiency. And the problem will be always the same, just to develop materials to work on this kind of temperatures. The first option you can think about is why not use ceramic materials. In this case, there is in this table, you can see here different ceramic materials like alumina, glass ceramic, hot-pressed silicon nitride, hot-pressed silicon carbide, and also a nickel alloy, a super nickel alloy. For example, from the point of view of density, if we are talking about aero engines, so it's very important that the density may be the lowest as possible. You can see that all the ceramics have low density if we compare, for example, with the metallic alloy. In relation with the melting temperature, of course, this may be as high as possible, and all these ceramics also have a quite high melting temperature. In the case of the elastic modulus, in general, we are looking also for materials with high elastic modulus, because in this case, under stress, the deformation of the blade will be the lowest as possible. All these ceramics also have, or most of these ceramics also have some very, very high elastic modulus. In relation with expansion coefficient, we are looking also for materials with low expansion coefficients, because in this way, as the blade is heated from room temperature to the highest or service temperature, the variation of the dimensions of the blade will be as low as possible. And all these ceramics also have quite low expansion coefficients. This other column are thermal conductivity. In this case, thermal conductivity is not a critical criteria, but also you can say that there are ceramics which have quite low thermal conductivity, and there are another ones which have quite high thermal conductivity. And the last column is fracture toughness, and this is really the main problem we have all these ceramics, that these ceramics have low fracture toughness, and at the moment they cannot be used because of this problem, because of this property, because there is an important risk to breakage during the service. By the contrary, these nickel alloys have much higher fracture toughness. This you can see there, and this is the material we are using at the moment. You can see that all the other properties are much lower than the ones of ceramics. For example, density is much higher, melting temperature is much lower, the elastic modulus in general also is much lower, the thermal expansion coefficient is quite high in comparison with other ceramics, but is this property which makes this the only material at the moment able to produce these blades. So here is the actual highest temperature which can attain these blades in gas turbines. It's about 1100 degrees. So here there is an important field in which new materials need to be developed in order to go to higher temperature, 1200 or 1300, in order to increase the efficiency of these gas turbines. There could be many more examples related, for example, to the chemical industry, petrochemical industry, glass manufacturers, metallurgical industries in general. Here is, for example, a picture of some of these petrochemical installations in which you can see that, not really seen very well, but here there are hundreds or thousands of tubes in which very high temperatures may be used. Also, these tubes are submitted to very high pressures. In general, we are looking problems with the temperatures higher than 1000 degrees. And also in these other industries, like glass manufacturers or metallurgical industries, we have also to take into account that not only we have to cope with very high temperatures, but also with contact with reactive chemicals, and also molten glasses, which are also very corrosive. slags and liquid metals, which are also very corrosive. And here there is a huge amount of different situations in which we need really the development of new high temperature materials. So, being the necessity of this, the developing of these materials in many different fields, let me now give you a brief overview of creep behavior, what is creep, which are the most important creep micromechanisms, and how can we use the micromechanisms maps in order to develop these new materials. First of all, I wanted to start with this slide in which you have the required properties to materials to be used at high temperature. Of course, we need materials with high melting points, that's obvious. There's also an important characteristic that materials made to have low diffusion coefficients. I am going to explain you in a moment that the diffusion is very closely related to creep strength, so these two things are very close together. Of course, we need materials with high creep strength. That is the main point I am going to talk to you in this presentation. But we need also other properties like high oxidation resistance, high hot corrosion resistance, depending on the environment in which these components are going to work. Another important point is we need that the material had the microstructural stability, and when we are looking with very high temperatures, this is not easy to obtain, because at this high temperature diffusion is important and the stability of the microstructure is not so easy to obtain it. Also, we have deal with other characteristics like thermal shock and thermal fatigue resistance, but because sometimes the temperature is not uniform, but there are some fluctuations in temperature, so it's important to use material with high thermal conductivity in order to reduce the thermal gradients, and also to use materials with low expansion coefficients in order also to reduce the thermal stresses. And not less important are toughness. I have related you the problem with the engine blades, where toughness was really a critical parameter. If we are looking about aerospace and things like that, of course, low density is also a very important requirement. And regarding cost, of course, the cost may be always as low as possible. Let me start now giving some overview of what is creep. So creep is the continuous deformation which a material a material submitted to applied stress at high temperatures. So, for example, if we take a sample like this one, we can heat the sample with an induction coil like this one in order to attain a constant temperature, and we applied a stress. In this case, it's a tensile stress, but we can apply also a compression stress or a flexural stress. The things do not change a lot. And in this plot, we can see how the deformation develops in front of the time. You have to take into account that the temperature is constant and the stress is also constant. So we can see that instantaneously here, there is some instant deformation. This initial deformation may be elastic or plastic, depending of this, if this stress is higher or lower than the yield stress of this material at this special temperature. But then, as you can see here, there is a curve in which the strain is growing continuously along this curve until the final rupture of the specimen. And this is a typical creep curve, which most materials behave like this one when they are tested at temperature higher than 0.4, the melting temperature of the material. So this curve has three regions: a first primary or transient region, a secondary or steady state region, and then a tertiary unstable final region. This third region is not a real one, because the problem here is that we are very near the rupture, so there are some internal damage in the material, so that in this region, the transversal area has changed, has reduced, and so the stress is not constant, but has increased because of the reduction of area. But if we maintain the stress constant, you can see that the secondary region prolongs to the final rupture of the specimen. And also there is this primary or transient region, which is a transient region. If we are speaking in general, this region is not very important because it elapses a short time. So the most important characteristic of this behavior is the behavior in this region, which is the secondary steady state region, in which, as you can see, this is a straight line, so that the slope of this curve is strain over the time, so is the strain rate. And this is the most important parameter, which is the strain rate of this material when we apply the stress in a situation in which the temperature is maintained constant. Here is, for example, the result, some results in which you can see here, this is the strain rate plotted against the stress, the applied stress at different temperatures. You can see here that, for example, we take this curve, we increase the stress, for example, for 3 to 6. There is an increase in the strain rate for 1 order of magnitude. So you can see that the influence of the stress on the strain rate is really very important, and can be expressed according to this equation, general equation, in which the strain rate in this secondary region is proportional to the applied stress over a coefficient n, and this coefficient n has a high value which can vary between 3 and 10 in general materials. Which is the influence of temperature? As you can also see here, this is a curve obtained for this temperature, 533 degrees, and this other one is for 644 degrees, so it's about 100 degrees more. And you can see that increasing the temperature 100 degrees, there is 1 to nearly 3 orders of magnitude in the increase of the strain rate. So there is a very high dependency also on temperature on this strain rate, which can be expressed by means of this exponential term you can see here, in which Q is a constant that is the activation energy for creep. A and N, of course, there are also constants characteristic of the behavior of this material in this special material. Another important point that you can see now in this other part of the picture is that if we divide this strain rate by the diffusion coefficient, this is the diffusion coefficient, which of course is related with the temperature according to this law. There you can see that the equation for the diffusion coefficient is also dependent of the temperature in a way quite similar to the creep. And what do we see? That the 4 curves go into a single line, in which there is a real dependency of this parameter exclusively on stress. So the dependence of temperature has disappeared. So when we divided this term by this other term, the thing which happens is that this term is the same, so that roughly we can say that the energy activation for creep is almost nearly or quite similar to the energy activation to diffusion. So diffusion and creep seems to be 2 phenomena very closely related. Let's now give you some small overview about which are the most typical creep micromechanisms. There are different ones. I am going to see you some of the most important ones. This is the power law creep, which takes place by glide plus climb of dislocations. You need to remember that the deformation by creep is a plastic deformation. So plastic deformation in general in a crystalline material is due to the movement of dislocation which glide along certain slip planes, typical in which structure. But the effect now of doing this experiment at high temperature is that this location can glide along this slip plane, and when they encounter, for example, here a precipitate or the particle, they cannot continue his way, and they stop here. So the deformation stops at this moment. But as we are at high temperature, there is another possible mechanism in which this dislocation can climb to another similar slip plane and continue his growth this way. So this is the mechanism of glide of dislocation along the slip planes and then climb to another slip plane when there is some obstacles in their way. So the expression which is related directly with this micromechanism is this one, in which the strain rate is directly proportional to the diffusion coefficient, and also there is a dependence of the stress over a coefficient n, which is between 3 and 8, as I have shown you before. There are also two possibilities regarding this micromechanism, which are named the high temperature creep and the low temperature creep. That is, high temperature is when the conditions are high temperature and low stress. In this case, the diffusion, which makes possible the climb action of the dislocation, is lattice diffusion. So this is the diffusion mechanism which is dominant. And in the case of we are dealing with lower temperature or higher stress, the diffusion phenomena is core diffusion. Here you can see, for example, this is a specimen submitting to the stress, and here is a typical arrangement of dislocation in the material, and here you can see the core diffusion, which is related to the core of the dislocation, and here is lattice diffusion, which is a more general diffusion process. Also, it's important to take into account that when we are dealing with temperatures that are higher than 0.6, the melting temperature of the material, some dynamic recrystallization can take place. And in this case, if this is the microstructure of this material, there can be some points in which the internal energy is the highest, for example, a triple point, a boundary region, as you can see here, where new grains are formed at the expense of the old deformed grain. So microstructure is modifying, and usually this new structure is less creep resistant than the last one. So this is a problem which is needed to avoid. Another possibility to creep deformation is diffusional flow creep. In this case, the influence of stress is much lower, and the deformation is due mainly exclusively to diffusion. You can see here that, for example, in this sample submitted to this stress, this is a grain, for example, and the deformation of the grain takes place exclusively because of the atomic movements from these areas to these other areas, and the grain will be elongating like this one. And this can be produced by boundary diffusion or by lattice diffusion. So the expression which takes into account this micromechanism is this one. In this case, the strain rate is directly proportional to the stress. In this case, the exponent of the stress is only 1, not 3 or not between 3 and 8, like in the other case. So the importance of stress is much lower. Also, the strain rate is directly proportional to the diffusion coefficient. But there is also here an important microstructure parameter which influences the strain rate, which is the size grain. So here is the size grain over 2. So in this case, in order to decrease the strain rate, we need to use microstructures with very high size grains, because as the size of the grain is larger, so the distances to go for the atoms in this diffusion process will be larger also, and the times will be longer, and then the strain rate will be reduced. In this case, we also can differentiate two different situations. At high temperature, the diffusion, lattice diffusion is the dominant micromechanisms, and if we are dealing with lower temperature, in this case, is grain boundary diffusion, the mechanism which dominates. Well, finally, the final rupture or final failure of the specimen would take place in different ways, but most of the usual ways may be these ones, in which in this case, in the boundary grains, they are form some voids. These voids are grow and then finally coalesce to make an intergranular failure. And in some cases also there are some grain sliding, and as a consequence of this grain sliding, some wedge cracks form along the grain boundaries, and also some intergranular fracture takes place. Let me introduce now very briefly the micromechanisms maps, which are very, very interesting in order to develop new high temperature materials. This, for example, let's explain that with an example. This is the map corresponding to pure nickel. In this map, we put in the vertical axis, we put the applied stress over the elastic modulus. The elastic modulus is a constant, so this vertical axis is related with the applied stress. And we have in the horizontal axis the homologous temperature, which is the service temperature over the melting temperature. Melting temperature is also a constant in a new material, so this axis is related directly to the service temperature. For example, and in this map, we have plot here the different micromechanisms. So in this area, we know that these are the most dominant creep micromechanisms acting in each area. So in this case, this part corresponds to power law creep, and this other part corresponds to the to diffusional flow. And also we have divided here the power law creep by the two different situations: low temperature creep in this way, and high temperature creep in this other region. So this is the micromechanism which dominates in each of these regions. And also with the diffusional flow. Here is also a differentiation between the low temperature diffusional flow in which the diffusion takes place along grain boundaries, and this is the high temperature diffusional flow in which the diffusion takes place by means of lattice diffusion. Let's, for example, take one case like this one. We can suppose that we have a nickel component if submitted to a stress that the stress divided by the elastic modulus is 10 minus 3. So this is the service point related to this condition. And let's say, for example, that in the case of the temperature, the applied temperature is the melting temperature divided by 2, so this 0.5. So with this temperature and with this stress, there is here a point which defines the situation of the component. And here you can see these lines, and these lines show you the strain rate. For example, you can deduce that under these conditions, a pure nickel component will have a strain rate about 10 minus 3 seconds minus 1. But not only that, you can see also that in this point, the creep micromechanism, the creep micromechanism which produces the deformation at high temperature is power law creep. So if we want to develop a material who needs to perform better than this one, we have to cope with this special micromechanism. I am going to give you some examples later on. This is a similar map, but now in the case of the alumina, because these maps are completely general. In this case, it's the same. This is the stress axis. This is the temperature axis. These are also the different regions in which some micromechanism dominates. This is the one related to power law creep. These here are the one devoted to diffusional flow, and also high temperature, low temperature, high temperature, low temperature. Here is also the recrystallization region, that in this case, to attain dynamic recrystallization is needed to go to very high temperature, 0.9 the melting temperature of the alumina. And this is the same conditions I have said you before, no? 10 minus 3 and 0.5, and in this case the point is this one, and you can see that if you use the alumina in these conditions, the strain rate is lower than 10 minus 10. So the behavior of alumina, of course, is much better than the behavior of nickel. But you can also see that the creep micromechanism is the same, is the power law creep. No. After this small overview, let me give you some practical examples, some design examples that have been used during the last years in order to develop new creep-resistant materials. Let's first of all, I want to show you the example related to the development of the blades used in gas turbines at the highest temperature levels. And to give you an overview of how these materials have been developed during the last 20, 30 years, let us start with the behavior of nickel. So let us say, what will happen if I made a blade, one of these blades made in pure nickel? So we can take the micromechanism map due to pure nickel, and this is the one. And here you can see which are the typical turbine operation of this kind of blades. So you can see here which is the temperature we attain in this special situation, and this is the stresses, which is depending of the size of the turbine and things like that. But in general, and to simplify, let's go to these parameters. So let's say that the stress over the elastic modulus will be 7 10 minus 4, and then the temperature over the melting temperature will be 0.5. In this case, you can see here, this is the temperature line, this is the stress line, this is the point, and this is the line which gives you the strain rate of a nickel blade at this special condition, which will be 10 minus 4. So with this data, we can extrapolate and make a simple calculation of the life of this blade working at this condition, because 10 minus 4 is the strain rate. We need only to know which is the maximum admissible deformation. Takes, for example, that the maximum admissible deformation of this blade will be, for example, just to give you an example, is 10%. Suppose that is 10%. So the maximum strain is 0.1 divided by T will be time minus 4. So we can have that the life of this nickel blade working on this condition will last only 1,000 seconds. So in a little about in less than 20 minutes, the blade will have this 10% deformation. Of course, this is not a good material to this application. But the important thing is that the creep micromechanism, which is acting over this blade at this condition, is power law creep. So is the movement of dislocations along their slip planes, and then the climbing of dislocation to the same slip planes in other positions. And so the way to develop a beta material is just to block the the movement of this dislocation. We can block it putting, for example, small particles or putting small precipitates all in this to block this movement. And that's the way the industry have worked. These are, for example, materials that are now used in these blades, which are based in nickel. The main component is nickel, but there are a lot of different alloys. Some ones, like tungsten, molybdenum, cobalt, and chromium, are used to make some solid solution strengthening in order to make difficulties to the dislocation to move. Another ones, like aluminium and titanium and niobium and tantalum, can be used to make these precipitates, nickel-3 aluminium or nickel-3 intermetallics, in order to block these dislocation movements. Some other elements with the carbon can be used to make some carbide strengthening, but the idea is the same, to put small carbides and to block this dislocation movement. For example, in the case of the nickel aluminium intermetallics, this is a diagram of the nickel and aluminium, and we are dealing, for example, with the nickel with 15% atomic of aluminium. We can heat this alloy to high temperature, 1200, 1300 degrees. In this case, we have only one phase, is the gamma phase, is the phase reaching nickel. We can quench this material in order to have this gamma phase at low temperature, but in a metastable structure, and then we can make an aging treatment between 700 to 900 degrees in order to make precipitate this nickel-3 aluminium, the gamma prima phase, which is the most important. These precipitates can block the dislocation movement. So doing this way, this is now the deformation map to one of these new alloys, in which the blockage, the dislocation movement have been clearly blocked. These are the same conditions I have before. This is 7, 10 minus 4, and this is 0.5. So now, as you can see here, the strain rate will be 10 minus 9. We have come from 10 minus 4 to 10 minus 9, so 5 orders of magnitude better behavior. This is now, we can now, doing the same, calculate the life of this blade made now with this alloy. 10 minus 5 will be equal to the maximum deformation admissible, 0.1, over the service life, T, and you can see that T will be now 10 over 8 seconds, will be about 115 days. So the result is much better, but maybe this result is not satisfactory at all, completely, because we want that these engines can work not only during days, but during years. So the way to do is to know which is now the creep micromechanism in this condition. You can see here that the creep micromechanism is not power law creep, like the dislocation movement is perfectly blocked in this case. But the problem is that in this condition, the micromechanism is diffusional flow, in which diffusion takes place along boundaries. So the problem to develop a better material than this one is just to decrease the number of boundaries. And the way to decrease the number of boundaries is to use the same alloy with a larger grain size. We can do that, for example, going to the manufacture of the blades. These blades are usually manufactured by means of casting and molding from a liquid alloy. In this case, this is the mold, this is the induction. Have lost the microphone. This is the induction coil. This is the liquid metal, and if we withdraw very slowly this mold downwards, we can promote some kind of oriented solidification, in which the grains are oriented in the direction of the blade. Here is, at the end, we have grains very elongated in the direction of the blade. Here is, for example, a picture of one of these blades, in which you can see this is one grain which goes from this end of the blade to the other end of the blade. continuously. And this is, finally, the deformation maps of one of these, of the same alloy as before, but now with a very large grain size. We put here the same condition, 0.5 T over Tm, and 7, 10 minus 4 in the case of the stress, and this is the point, the service point. You can see here that this is 10 minus 10, so the strain rate is lower, much lower than 10 minus 10. So we have achieved an improvement of several orders of magnitude again. But suppose that we want to obtain an even better material. So which is the creep micromechanism which is acting in this point? So you can see that it is the same. It is diffusional flow, and in this part is boundary diffusion. So there is diffusion along these boundaries. So how can we cope with this problem? The way will be, the better way will be to completely eliminate these grain boundaries. So to make a blade monocrystalline. And this is the way these blades are made at the moment. This is a small scheme of how this can be made. This is the same scheme as before. This is the grains which are growing in this oriented solidification. You can see the grains are growing, and here there is some stopper that can stop the growing of these grains. Here also these grains are stopped here, and here there is a channel in which only one grain enters. You can see here, only one grain is entering here. This is this channel, one grain is entering here, and this grain fills completely the mold. This is the way to obtain a monocrystalline blade, which is the best option we have at the moment. I don't know if I have time. 5 minutes. Okay. This is a second example. I am going very quickly. This is a quite common example, but it's also interesting that is related to the tungsten lamp filaments. So the normal lamps are made with tungsten filaments in which some electrical intensity passing in the filament makes the light. But it's important to consider that the working condition of this filament is extremely severe, because the temperature is 2,400, 2,500 degrees. So there are not many materials we can maintain these temperatures during the design life of one of these lamps, which may be about 1,000 hours. Here are some geometrical parameters related with this special situation. So the material we usually use is tungsten, because the melting point of tungsten is much over 3,000 degrees. But the problem in this case is a creep problem, because as you can see here, this filament is winded, and it is retained by two supports, or by different supports, and between these supports, the filament is deforming by means of creep due to the own weight of the filament. In this case, there are not external weight, but the only weight, not external loads, but the only load is the weight of the filament. And you can see here there is a load, small load, but there is a load, and there is a very high temperature here. So there is a creep micromechanism which is acting. And finally, the problem will be that the spiral will deform, and finally, one spiral contacts with the adjacent one. Here, a hot spot is formed, and the breakage of the filaments will take place. So at the end, the problem of this lamp is a creep, really a creep problem. So it is quite easy to find which is the maximum allowable strain rate possible, because we know the geometry of this winding. We have the distance between the two adjacent spirals, and we know that the maximum the time that the lamp must last may be higher than 1,000 hours. So at the end, we can finally find that the maximum strain rate will be lower than 10 minus 9 seconds minus 1. What happens when we use a pure tungsten filament? So this is the micromechanisms map due to tungsten. In this case, this is the conditions of different lamps, one with 25 watts, other one with 40 watts. There are quite different importance in the stress situation because the geometry of different lamps is different, but it's not important that. But the main important point is that this is 10 minus 9. You have to remember that the strain rate may be lower than 10 minus 9, and there are a lot of conditions in which, of course, this is not accomplished. So there are a lot of conditions in which the strain rate is much lower than 10 minus 9. So the lamp will last not 1,000 hours, but much less. But if we regard also to the creep micromechanism, we can see that the creep micromechanism in this area is power law creep. So the way to cope with this problem is always the same as we have seen before. So is to put some particles in order to avoid or to impede, to block the dislocation movements. For example, using, what we know as doped tungsten, which is tungsten doped with small particles of alumina, silica, or potassium oxide. And this is the final map of doped tungsten. These are the similar conditions I have shown you before, and you can see that now all these conditions are clearly below 10 minus 9. So all this material can be used to make this filament, and this lamp will last more than 1,000 hours. So let's, as the time is over, let's go to the conclusions. First of all, or some summary. First of all, I wanted to emphasize that the efficiency of many industrial installations I have shown you that is highly dependent on the development of new materials with higher creep resistance. We have seen several examples in the chemical field, petrochemical field, also in power plants, aero engines, glass manufacturers, metallurgical industries, etc., etc. There are a lot of examples. One important point is that the development of such new materials need a full understanding of the creep micromechanism acting at each particular service condition. It is essential to know which is the micromechanism in order to go to avoid it. And the way to do it is doing microstructure modification. So this is the way to produce new creep-resistant material. I have shown you several examples. And finally, nanomaterials, and especially nanocomposites, will surely be the way to solve many of these industrial problems. This is an important point in which many research efforts must be made during the last years, and I hope that most of you can, or some of you can solve one of these problems, for example, doing this kind of research. Thank you very much.